I'm going through the answers quickly for anybody who needs them. Go ahead and pause it and you can check. And we're done. Okay. Alright, cool kids, here we go. 7-3. What did we decide yesterday? Which one's easier? So much easier. Ready? I want you guys to grab out your calculators. I want you to, since you did not see matrices last year, this is the first year I've had a pre-calc class and never seen matrices before. It's kind of exciting, actually. You're not all trying to cheat from the very beginning of this section. Anyway.
Because they wanted us to do it.
Alright. Long story short, calculators out. I want you guys to go find at least one calculator per group. Make it visible for the rest of the group. If you don't have one, look behind, look aside, look in front of, etc. Where can you find matrices on your calculator? Not in apps. It has its own menu. I want you to put this system of equations in a matrix. I want you to put this system of equations in a matrix. P.S. You have to make a matrix first. You have to make it of the right size. Has anybody found a matrix menu?
Second matrix.
What have you figured out? How do you make one?
Go to edit.
Edit. Good. Now what? Oh, he's too small. What happens if you start making stuff? Ooh. But I don't want 2 by 2. How many thingies do I need? How many spots?
3 by 3.
No, not 3 by 3.
3 by 1.
I need to get all the numbers in.
3 by 1.
No, I need to get all the numbers in.
4.
3 means 3 rows, right?
Okay.
Why did someone say 3 by 4? Because I need 3 rows and an X column, a Y column, a Z column, and a number column.
So do we put in like 1, -2, 3, 9?
Put it in your matrix. Wait, but X's and Y's, don't put in the X's and Y's, only put in the coefficients. Whoa, what do you do for the Z that's not there?
0?
Yep.
Oh, you're just being a pain.
Colby's not even in your group, that's the funny thing. David has a calculator.
He's just rough with it.
Alright, you guys got your matrix in?
Yes.
No.
Stop judging. Be considerate.
So we plug it in, press second.
Okay, do you guys remember how we said we liked the second form better?
Oh, we're supposed to plug in this.
And yesterday I was saying stuff like... Thank you. Yesterday I was saying stuff like, if you were to approach this problem and I just told you, go find X, go find Y, go find Z, all of you might decide to do it different ways. One of you might see the X and negative X and be like, hey, I'm going to do elimination with these two, cross that out, and then keep going. Someone else might say, hey, I see these two, the Z's I can get to cancel by multiplying this guy by 5 and that guy by -3, and that would be good. Somebody random might think to do something with the Y's, I don't know who. Anyway. But you would have different approaches to solving because there's not just one set way to go. But then I said, but we have these cool things these days called computers. And to get a computer to do what you want it to do, especially if you're trying to make it do something new that maybe no one else has ever made it do before, that's where the money comes in, right? You got to tell the computer what to do, and it needs a systematic approach to the programming where it could take any system of equations, no matter how nasty or gross, and always put it into a nice, quickly solvable form. But to do that, you can't just go attacking a problem however you want. You need some sort of system, systematic approach, some sort of system that will always work. And here's the crazy thing. Someone has done that system and programmed that system into this calculator such that, ready? I want you guys to quit. I want you to go back to the matrix menu. I want you to go over to Math. I want you to go find the REF, row echelon form. REF, just one R. Just one R. There he is. You see it? REF, row echelon form. Is there a system that could take any nasty set of 3, or if it was bigger, 4 or 5 or 6 equations and put them into this nice form that you would like to solve? Hit that REF. Oh, wait a minute. It needs somebody to do REF too. Oh, didn't we just put our matrix in matrix A? Sweet. Go grab that name and then tell the calculator to go do the system. Ooh. Guess what the system is?
Wait.
Wait a minute. Is it a little different?
Yes.
What's a little different about it?
0.5 off.
Okay, so hold on. What could have gone wrong? What's the struggle? Can there still be user error? What does that mean? Are all my terms right? I have 1, -2, 3, 9? -1, 3, 0, -4, 2, -5, 5. Huh. Am I wrong?
No, it's just another form of the problem.
Is it? How can we tell? Is this the X column? Is this the Y column? Is that the Z column? Does Z equal 2? Okay. What would go on here? 1Y plus 5Z equals 9. Okay, so hold on. So if Z equals 2, we can plug it in here, right? 3 times 2 is 6. Subtract what's 5 minus 6?
-1.
-1. Okay. What's 5 times 2? What's 9 minus 10?
-1.
Oh. Okay, so what's going on here? If we plug in 2, that's 6. If we plug in -1, that's positive 2. 2 plus 6 is 8. 9 minus 8 is 1, right? Pause. Yeah, a couple of you agree? Okay, so 6 and then positive 4. 6 and 4 is 10. 9 minus 10 is -1. Okay, so if I plug in my, ooh, this is going to be nasty. If I plug in my 2, 5 halves times 2 is 5. Negative 5 halves times -1 is positive 5 halves. Positive 5 halves and 5 would be 15 halves. This is rough. 17 halves minus 15 halves would be -2 halves. No. Did I do it wrong? Hold on. 5 and -5 halves, -15 halves, 17 halves. Oh. I think it works, it's just grody. You know what we could do? We could go ahead and do this and say, I don't like decimals. Well, that's prettier. 2, that'd be 5. -1, that'd be positive 5 halves. Positive 5 halves. 15 halves. 17 halves minus 15 halves is 1. I think it works. 6, 4, 6, 8, 9 minus 8 is 1. Okay, whew, there we go. 1 equals 1, we're done. So pause. What do you guys just learn? Can a calculator do row echelon form?
Yes.
Yes. But how can it do row echelon form? Because somebody somewhere programmed it to do it. And how did that somebody somewhere program it to do it? Teach it about systems and teach it about elimination and say, hey, when you look at a matrix, go the way that you would like to go the best. You have to give it a systematic, step-by-step way of attacking a system of equations such that it'll always be able to get to the REF form. Where you can say, hey, answer, go back, plug in. Hey, answer, hey, go back, plug in. Hey, answer. Do you think maybe somebody said, wait a minute, it's super easy to solve from here, and it's super systematic, like plug in the Z, then plug in the Y and Z and be done? Do you think there's a way that the calculator can keep going to find the X and Y and Z? Definitely. But that's not our goal today. Our goal today is to figure out what is a way to think like a programmer to say, here's a problem that can change how it looks from one problem to the next, but a few things stay the same, and how do I then make a system that I could plug into a program to have a calculator solve it for me, or to have a computer solve it for me. Maybe it'll take longer in the short run, but in the long run, you'll be able to have the thinking that, well, basically has gotten many people quite far. So here we go. Let's go ahead and talk about row echelon form. Trying to think like a programmer. Trying to think like we're not just facing the problem that we're looking at, we're facing it, well, in a sense, we're facing all problems similar to but different from the one that we're looking at. And is there a way of developing a system that will always work? Not just trying to take the shortest way for each problem as it comes, because that's where we're going to be stuck having to do everything by hand all the time. But instead thinking, can I come up with a system that could lead to a program that could lead to this whole process being able to be solved for me from here on out? So that's the Gaussian elimination. Gauss, you were the mathematician. Hey, scientists too. We're not going to go into his history today, though. Row operations. If you guys were noticing when you were in your calculators, and we went to that whole second matrix math menu, most of you might not have gotten this far, but if you go to the very bottom, do you see row swap row plus times row plus? Guess what? These are row operations. So row operations are kind of the building blocks of this whole systematic approach to matrices, which is really just a systematic approach to having a computer solve systems of equations for me. First of all, we're totally allowed to switch around two equations, totally legal. We're allowed to multiply whole equations by a non-zero constant. We already know that. We're allowed to add a multiple of one equation to another to replace. Meaning, if we want to change up a system, if we want to actually do operations to help us out, any of these three things are legal. We've totally done this with elimination, and we've totally done this with elimination. We haven't really done much of number one, but it will be helpful once we get there. Long story short, once again, we're trying to figure out a systematic approach to solve any and every system to be able to then give that systematic approach to a program and say, hey, do it for me. So I say there's a chain game to get to the stair-step system. There's a chain game to get to row echelon form. We see the benefits of this form because once you get it to this form, it's like super easy to solve. We already have one plug-in, we have the second plug-in, both we have the third. We could do that, we could tell someone else to do that, we could tell a program to do that if we could only learn some basic programming language. So here's the idea. In this system, the one that you just saw, the calculator put into REF, you saw the book put into a different REF. How could we attack this not with our creativity and saying, oh, I don't like the X's, let's get rid of them, or oh, I don't like the Z's, let's get rid of them. Not with our creativity, not with the perspective of, I want to get through this problem as quickly as possible, but with the perspective of, okay, given any sort of problem similar, what could be a way of tackling it that will always work? That I could repeat time and time and time again. And here's the system. The system says, well, one way of doing the system says, take the first two equations. System says, take the first two equations. We're going to use our creativity at first. We're not going to go straight to the systematic that will always work, but we'll use our creativity a little bit first. If we were to take the first two equations, kiddos, could I just do elimination right now? And if I did elimination, and if I tried to eliminate the first variable, saying, well, he's in my way to trying to solve, I would just go ahead and add the 2, right? So if I add the 2, can we try to do mental math a little bit? What's x plus negative x going to be? What's negative 2y plus 3y going to be? What's 3z plus 0z going to be? Equals? Wouldn't it be nice if we could have another equation with just y's and just z's? Right? But struggle, in order to get that, first of all, system, let's just take the next 2 equations. We can always take the first 2, we can always take the next 2. The struggle is, can I just add the 2 together now? But what can I do? Why are you multiplying this guy by 2? Because you see the 2 here, you need them to match, right? Remember, you're trying to think of whatever this looks like, however nice or not nice it is. Systematic approach. So if I multiply this guy by 2, who else do I have to multiply by 2? This guy and this guy. And remember, the negative was already there, so I'm just multiplying by 2. Now, is that a little dangerous? Yes. Could you write the whole little multiplication of 2 right here? Yes. Could you rewrite both equations to make sure you're not making any mistakes? Yeah. But either way, when I go to add, and to be honest, if it's a little bit easier for you, since we do have to multiply something together, we could go ahead and say, all right, let's go ahead and do this elimination-y thing, but I'm just going to go ahead and make sure that I'm not doing anything wrong. I'm going to multiply everything by 2. There we go. So I can see it nice and clearly. Add those 2 together. What do I get?
Y plus 5.
Yeah, y plus 5z equals 9. Now this one was super basic in the sense of the first one, something just canceled out right away. The second one, we only had to multiply one equation to make it cancel out. We know that sometimes that could get harder. But maybe there's a way you could always get the first 2 to cancel out the x term and the second 2 to cancel out the x term. And if we can always do that, what can we always do next? Take these 2 and cancel out. Now this one, once again, is pretty ideal because all we need is to make one of these opposite, right? So if we make all of these negative, then what's y minus y? 0. What's 3z minus 5z? What's 9 minus 5? What just happened? I just got my stair step. What do you mean? Well, don't I have z equals 2? When you guys look at your stair step, do you realize the bottom one just has a z, the one above just has a y and a z? And the one above that has an x and a y and a z? And how could the calculator program be a little different than the one they wrote down? Couldn't you have chosen a different y and z one? Pause. Look at your notes. Which one did it choose for the second stair step? This one, right? Look at your calculator. Which one did it choose? The other one. It had 1 and 5 and 9. Oh, but does it really make a difference? No, both of them are going to work. They're both fine. They're both out of the system. How about the other one? You could have chosen this one or that one. Well, that one's kind of awkward. Or that one. You could have chosen any of them. The calculator system just decided to do things in a little different order than maybe the next system did. Do we have row echelon form? Yes. How do we finish once we have that nice stair-step pattern? Back substitute and say, you know what? This is a 3-dimensional system, right? You guys know x, y, z, a 3-dimensional point. Z is 2. We already figured out if you go back and plug in 3 times 2 is 6, subtract y is negative 1. Go back and plug in 3 times 2 is 6, negative 2, negative 1 is positive 2, that's 8, 9 minus 8 is 1. I did it fast, you take your time, get it right. Yeah? Take your time, get it right. But do you know what I did?
Yeah.
Right? I plug Z in, and once I found y, I plugged y in 2, and then I found x. Okay, back substitute. There we go.
Are we ever going to have to graph these?
Three-dimensional points? No, we don't really go into that. There is a whole chapter of three-dimensional vectors in chapter 11. But since we're not specifically a pre-physics class, I don't really go into it. It's there, but I don't like to go into it. Okay. It's cold. I'll go check the thermostat, but meanwhile, what's all this for? Pause! My artistic ones. Could you have fun sketching these for a few minutes, couple minutes? Yes. My non-artistic ones. Could you just write down in words what you see? Why on earth are we talking about three-dimensional pictures?
There's a Z.
We have an X and a Y and a Z. We're talking about three-dimensional equations. So hence we're talking about how planes are intersecting, not just lines. Ready, set, either write in words what you see under the consistent, inconsistent columns, or have some fun and try to draw the pictures. Go. Or both. Even the pictures will probably have a few words. Alright, it'll get warmer. Hang in there. Yes, guys, have we talked about consistent and inconsistent yet? Yeah. Consistent, doesn't that mean finitely many solutions? Ooh, I wonder if that still works on this one. Inconsistent, doesn't that mean no solutions? It kind of works here, kind of doesn't work. Three planes only intersecting in one point. I think that's how I would do it. Because like pink and blue is intersecting in a line, pink and yellow is intersecting in a line, yellow and blue is intersecting in a line, but all three only share one little point. Looks kind of like a star, but that's only if you look at it two-dimensionally. Three-dimensionally, I think most of you guys can tell it's three planes, right?
Which one are we talking about?
The first one. The solution 1.1.
And for the second one, for consistent, would be three.
In one line, yeah. You could say sharing one line, intersecting one line. Pause! Look at the pictures, or the non-pictures in your group's notes, and tell me if you have someone autistic in your group. It might not be you. People are humble, they might not tell me. Raise your hand if you have someone autistic in your group.
I'm still in the second
Alright, finish up.
Patricia's a beautiful.
I know. It's just when they all meet up. Is Ryan artistic?
I'm just looking. Jax is actually going pretty well. If you actually tried to draw this, or draw these, you should have a donut hole on the way out. Anyway.
Oh, really?
On the way out, on the way out, on the way out. If you decided to try to draw them, I give you props. Okay, I'm going to move on though. But pause. Pause, pause, pause. Can I technically say that consistent is finitely many solutions anymore? Because remember, didn't he say equivalent is infinitely many for elimination? And didn't we say that inconsistent is none, and so consistent must be finitely many?
Yeah.
What's the struggle? Can I say consistent is finitely many anymore? First of all, this one I would call equivalent. Why am I calling this equivalent?
Are we talking about the one?
It's one plane, but do you see how there should be three?
Yeah.
What does that mean? They're all the same. They're all the same plane. The struggle with consistent is basically solutions exist. For elimination, we use different words for consistent and equivalent. So equivalent we said was infinitely many. But technically, if you guys notice here, equivalent is underneath consistent. So consistent, now that we've seen kind of a different explanation for it, consistent just means basically solutions exist. And in a three-dimensional system, it could just be one point, it could just be one line, or it could be all points on one plane, and that would be the equivalent. So basically, consistent just means solutions exist. Equivalent is one special case where all the points of one will equal all the points of the other, not just some points. Inconsistent means no solution. And we know that that one happens when we get something that's false, right? And then let's see, where was the true statement? False was no solution. False was inconsistent. Where was the true statement? Who would he be? Put him right here for right. Carl, you had a question, bud. What was it?
How would you describe the inconsistent the second one?
Yeah, TP, that one works. The three planes intersecting two at a time, or we could say the three planes intersecting but leaving space in the middle. So long story short, all three will not come together. Basically, there's hollow space in between. That's the best way of putting it. Hollow space in between. Reminds me of, like, I don't know, you guys used to probably do the playing card, like, structures, right? Trying to make the towers, like the Uno cards, or three of you. Okay. Whoops! Uh-oh, I'm missing my example.
I like that.
You like that? That's a good one. Party pooper. Alright, so,
Get out by ourselves.
make it up.
Yeah.
The struggle is if you, we might do that, but the problem is you guys have seen me make a hard problem. Doesn't it usually end up kind of in failure? Because if I make it up, it could get or be a lot harder.
Make a better metaphor for life.
We should, just maybe not right this second. Let's get a little bit more skilled first. Number 32, here we go. 2x. Oh, this one's still kind of easy.
Isn't that a good thing? No, what?
Well, we'll see what happens. I think I have this one for a reason. 2x
She's good at what?
plus 1. That is a lie. Okay, 2x plus 1 plus 3z equals 1. Yes, if you guys are writing these homework problems, please double check you're writing down the right one. I've had so many people write down the wrong one, and they're kind of wrong, and you would be very, very sad to figure that out later. Well, if you can't get the right answer, that's not usually a good thing. 6x plus 8y plus 18z equals 5. Let me double check. So I want you guys to do it together. Because remember, all of you have done this before. You start writing on one problem and end up writing another problem and you don't figure it out till later. Yeah. So sad. 2x plus y plus 3z equals 1. Check. 2x plus 6y plus 8z equals 3. Check. 6y plus 8y plus 18z equals 5. Remember your objective. The goal is not to get there the fastest on this one problem. That would be a very short-sighted goal. The goal is to have a system that will work every time. And P.S. what we did last time would not work every time. If it doesn't work, just to subtract the first two every time. Oh, this one's very simple.
Subtract the second.
I guess you could put in a problem if the two coefficients are the same, then go this way. If they're not the same, then I guess you could flip through it. You see the system now? I'm taking the first two. Guess what I'm going to do next? Next week. Would you guys multiply the middle one by 3 for the second step? Yeah. Sorry, I already did the negative in there. Yeah. Negative 3.
You see, sounds good, right?
It happens. 18 minus 24. I'm following the system, so did the first two and the second two, needing the x terms to match. So I multiplied this guy, the 8 by negative, and then 3. I think I multiplied everybody by negative 3. Yeah. And then 18 minus 24 is negative 6, right? I'm going to go ahead and multiply this whole guy by 2, right? Good, negative 2. So I'm going to have my positive 10y plus 10z equals 4. What do we get?
2.
Yes.
Don't I get 4z equals 0? Right? Yeah. Hold on. I put a negative for everybody. So I did 0, negative 5, negative 5, negative 2. Oh, that would work. That's not going to be wrong necessarily. You should get z equals 0 also. What Thomas is saying is for his, he decided to put a negative next to everybody on the top. Now, here's a dilemma. We're both following the same system. Take the first two, take the second two. But is there still some variation? Yeah. Oh, wait, when you guys did your calculators, didn't all of them go the exact same route to their REF one? Yeah. Which means even if the system is still somewhat consistent, no, I shouldn't say consistent, stink. If the system is, even if the systematic approach has the same basic pieces, we still could have some variation on what's going on. Which isn't going to work for your calculators because we need something where it goes the same way every single time. Interesting. Anyway, do we have our stair step? Yes and yet no. Yes and yet no. We have z equals 0. Here's the struggle. Ready? Can you guys look at your calculators again real quick? At the REF that we did? That was this guy, right? I wonder why his was so much nastier than the books. We already talked about where this guy came from. It was z equals 2, right? We talked about where this guy came from, in that he just, the computer programmer, oh no, that's the end of the notes? That's lame. Hold on.
My calculator just turned blue.
It what?
It just turned blue.
Oh, undo second and then the down button. Second down, second down, second down. Does that lighten it?
Oh, there you go.
There you go. You can change the contrast. It's weird. Yeah. Okay, kiddos, hold on. The 1 and 5 and 9, didn't that come from this one? We're trying to figure out how the program came about. The 1 and 5 and 9, right? That came from right there. Where on earth did the 1, negative 5 halves, 5 halves, 17 halves come from? Not that guy, not that guy. What did, wait, negative 5, 5, 17, but what did this do? Divided everybody by 2, and here's why. Proper REF form. Check out the book's REF form. Proper REF form needs leading coefficients of 1.
Oh.
And the program didn't know, wasn't told, to just pick the one with the beginning coefficient of 1. It just has a system where it just takes a certain equation and then makes it a 1. Interesting. Why am I bringing that up? Proper REF form is not only stair-step, but also leading coefficients of 1. What are we going to have to do right now to make it proper REF form?
Divide by 2.
Not divide by 2. I have my z equals 0. My next step is I need to go to my y's, but I don't want to use him or him or him the way they're written. Because I need to divide either everybody by -5, everybody by -10, or everybody by 10. What do you want to do? Yeah, I thought so too. I'd probably pick the 5 for sure, but either way. Divide everybody by 10. All right, cool. So 10y over 10 would just be 1y, right? 10z over 10 would just be 1z, true? And then 4 over 10 would just be 2/5. All right, how do we get my top equation?
We get divide by 2.
Yep, divide everybody by 2. So I'll have x plus 1/2 y plus 3/2 z equals 1/2. Pause. Put this system into your calculator and let's see which route it chose to take. Remember trying to figure out where the programming came from. Plug in the original matrix, do REF, and let's figure out where the programmer went. We're doing systematic approaches, kind of, but we're still, as we kind of talked about, we're still kind of having some variations, which means we're not quite ready for programming.
Wait, so how did we get one person?
Everybody chose, not everybody, Patricia wanted to use that one, so did me, so did I. But we decided to take this guy and divide everybody by 10. We could have divided everybody by -10 or divided everybody by -5. We had to get a leading coefficient of 1. That's proper REF form.
So why is the first one divided by 2?
Oh, because we couldn't have the 2 stick around either. We could have taken this guy and divided everybody by 6. Could have done that too. You guys sort of in your calculator trying to figure out his programming? I think it's still a 3x4, right?
Yeah.
I just really did all.
I gave them all? No negatives, right? Not yet. Hold on, I want to see what he looks like.
1, 4, 3,
1,
3 or 5.
Remember, you can go fractions. Oh, what route did it go? Did we use the last one again? I think I figured out its programming. I think it's always picking the last one. Anyway, we'll figure a little bit more out tomorrow. Because, to be honest, we're basically done with milk. But we'll do a little bit more so that you guys have this homework due not tomorrow but Friday. But we're starting 6-5, no 7-4 tomorrow. Bye, guys. 7-3 due Friday, but you can basically do it all. I'm just giving you a little bit of grace and let you spread it out. Definitely start tonight.
Victor, give me a drawing. Drawing. I do.
Oh yeah, we are. Oh, wait. We're ready for 7-3A. Sorry, do 7-3A. Don't do B yet. That's the one we're not ready for. Sorry.